We turn now to nanomaterials, and in particular I want to emphasize the physics behind nanostructuring rather than specific applications, because the applications of nanostructuring are developing so rapidly. In general, one nanostructures materials in order to make some dimension smaller than a critical length scale important in the physics of the phenomenon one is trying to control. If one restricts all 3 dimensions, one has a quantum dot. Restricting 2 dimensions, one has a nanowire. And restricting just 1 dimension gives a planar structure, superlattices and heterostructures being an example. Length scales that can be controlled vary all the way from electronic to that of light, as in the case of nanophotonics. We'll talk also about magnetic nanostructures, where many scales are relevant, thermal devices, and then finally nanofluidic devices. As a separate little topic, we'll also discuss the way in which nature can point the way to nanostructuring as we copy nature's nanomaterials in a process called biomimetics. So what is the important length scale that controls a particular phenomenon? We already saw in chapter 7 that one important length scale is the Fermi wavelength of electrons, which is very short, of course, atomic dimensions. I'm putting down just one example here, but typically a few angstroms. Another important parameter is the mean free path between collisions according to the Drude model, and this can be several hundred nanometers at room temperature. So nanostructuring on both of these length scales can be important. For example, the Landauer resistance that we spoke of required wires of at least a few angstroms dimension to support a quantum channel of transmission, but less than the scattering length so that transport was not like an ohmic resistor, but dominated by quantum mechanics. In the case of optical devices, one gets down to nanometer dimensions, so the wavelength of blue light, for example, is about 400 nanometers. If one looks at the half wavelength, which is the relevant parameter for most physics, and considers a refractive index of perhaps 1.5, then this brings you down into the length scale of 100 nanometers or so. In magnetic interactions, the way in which electron spins are flipped to ensure that the wave function of electrons is antisymmetric under particle exchange is essentially local and atomic scale. On the other hand, clusters of magnetic material form strong magnetic dipoles, and these have interactions which, as we know from chapter 4, fall off as 1 over r to the 6th. In thermal interactions, the mean free path of a phonon, or thermal vibration, can be hundreds of nanometers at room temperature and become macroscopic at very low temperatures. In the case of fluids, there are 2 critical length scales. One is set by the so-called Reynolds number, which has to do with the ratio of inertial viscous flow. Flow is always dominated by viscosity in small structures. The nanostructuring is important when the dimensions of a channel become comparable to that of a molecule in the fluid, or even at a smaller length scale, the way in which the fluid sticks to the nanostructure is altered by the dimensions of the nanostructure. We turn next to consider the density of energy states available in nanostructures, and to introduce this topic, I've shown here what happens as an atom interacts with a second atom to form antibonding and bonding states, and then 2 pairs of atoms are brought together to form a cluster of 4, so these states then split again, and so on. What happens is the strongest interactions dominate the splitting at the edges of the band, which is largest. And so now when you have a very large number of atoms, one develops the conduction and valence bands from the antibonding and bonding states. But in a nanocluster, you'll have a structure with a band-like structure near the middle, but discrete states at the edge. In the case of a metal in which the band is half occupied, the existence of these discrete states is not important until the cluster becomes very small. In the case of a semiconductor, where the carriers are either holes in the top of a valence band or electrons at the bottom of a conduction band, nanostructuring changes the properties of the material in larger structures. I've shown down here schematically the energy density of states versus energy, and we'll talk about this now in the slides that follow. We derived the density of states per unit K in Chapter 2, so just to remind you, this result was obtained by taking 4 pi vk squared dk and dividing it by 2 pi over L all cubed. We want, however, now the number of energy states, or the number of energy states per unit energy. So we can obtain this by multiplying dN dk times dk dE, inverting this result here. In this expression, I have obtained dk dE, or dE dk, by taking the derivative of the expression for the kinetic energy of free electrons, and then dN dE just follows as dN dk times dk dE. When this is done in 3 dimensions, and the expression for E derived from K using this free electron kinetic energy here, one obtains a density of states per unit energy which varies like the square root of energy, which is the shape of this function down here. In 2 dimensions, the density of states per unit K is just proportional to K, and so this cancels out with the 1 over K that appears in the expression for dk dE, with the result that the density of states is constant. This is shown by these flat plateaus here for different SPD and so on states of the material. In 1 dimension, we have no dependence on K at all for dN dk, and this means therefore that dN dE varies as 1 over the square root of E, and this gives rise to these singularities here at the bottom of bands as E for that band goes to 0. And then of course in 0 dimensions one has simply a series of molecular states. The goal of density of states engineering by nanostructuring is to squeeze a larger number of states into some desired energy range in order to make a material do the desired thing.